Caustic corrosion damage mechanisms as a part of uniform or localized loss of thickness. Description of caustic corrosion based on API 571, localized corrosion due to the concentration of caustic or alkaline salts that usually occurs under evaporative or high heat transfer conditions. However, general corrosion can also occur depending on alkali or caustic solution strength. Number 1 is caustic corrosion damage definition. Caustic corrosion refers to the degradation of materials, typically metals, due to the corrosive effects of alkaline substances, specifically those containing hydroxide ions, OH. This type of corrosion is often associated with environments where caustic substances, such as sodium hydroxide, caustic soda, potassium hydroxide, or other alkaline solutions, are present. Caustic corrosion is particularly significant in industries that utilize strong bases, such as chemical processing, pulp and paper manufacturing, and petroleum refining. Number 2 is mechanism. The caustic corrosion process primarily occurs when metal surfaces come into contact with a concentrated alkaline solution. The presence of hydroxide ions can lead to several corrosive mechanisms, including Number A of corrosive mechanisms is anodic reactions. Metals can undergo oxidation, releasing metal cations into the solution. In alkaline environments, this is influenced by the high concentration of hydroxide ions. Number B of corrosive mechanisms is localized attack. Caustic corrosion can cause localized attack, often referred to as caustic stress corrosion cracking, SCC. This phenomenon occurs when stress is applied to susceptible metals, resulting in the formation of cracks that propagate through the metal structure. Number C of corrosive mechanisms is intergranular corrosion. This type of corrosion may occur along the grain boundaries of metals, especially for alloys, leading to material failure without significant overall weight loss. Number 3 is affected materials. While many materials can be affected by caustic corrosion, certain metals and alloys are more susceptible, including carbon steel, commonly used in various applications but can suffer from caustic corrosion, particularly in high-temperature and high-pressure environments. Certain stainless steels. While stainless steels have good corrosion resistance, certain grades may still be vulnerable, especially when exposed to elevated temperatures and stress. Copper and alloys. Copper and its alloys may experience accelerated corrosion when exposed to caustic environments. Number 4 is conditions that promote caustic corrosion. High pH levels. The corrosivity increases significantly as pH levels rise, particularly above pH 12. Temperature. Elevated temperatures can exacerbate the effects of caustic corrosion by increasing reaction rates. Aeration. The presence of oxygen can facilitate electrochemical corrosion processes. Concentration of caustic solution. Increased concentration of hydroxide ions enhances corrosion rates, particularly in closed or poorly ventilated systems. Number 5 is consequences of caustic corrosion. Number A of consequences of caustic corrosion is material weakening. Structural integrity diminishes over time due to material loss, leading to failures that can result in leaks, bursts, or catastrophic failures in critical equipment. Number B of consequences of caustic corrosion is increased maintenance costs. Regular monitoring and maintenance are required to manage caustic corrosion, leading to higher operational costs. Number C of consequences of caustic corrosion is safety hazards. Structural failures can pose significant safety risks to personnel and can lead to environmental contamination in the case of spills. In summary of this description, caustic corrosion is a significant form of corrosion that can impact the performance and safety of metal structures and equipment in caustic environments. Understanding its mechanisms, influences, and mitigation strategies is essential for effective corrosion management in industrial applications. Caustic corrosion affected materials based on API 571, primarily carbon steel, low alloy steels and 300 series SS. Caustic corrosion can affect various materials, particularly metals, and their alloys, when they are exposed to alkaline environments, especially those containing hydroxide ions, OH. The following materials are commonly affected by caustic corrosion. Number 1 is carbon steel. Carbon steel vulnerability. carbon steel is particularly susceptible to caustic corrosion, especially in high-temperature and high-pressure environments. Carbon steel consequences: corrosion can lead to pitting, loss of structural integrity, and potentially catastrophic failure if not monitored and maintained. Number 2 is stainless steel. Stainless steel types affected: certain grades of stainless steel, particularly those that are martensitic or ferritic, can exhibit susceptibility to caustic corrosion under specific conditions. Stainless steel mechanism: localized corrosion, such as stress corrosion cracking, SCC, can occur when stainless steels are exposed to high pH environments combined with tensile stress. Number 3 is copper and copper alloys. Copper and copper alloys vulnerability: copper and its alloys, such as brass and bronze, can corrode in caustic environments, particularly when exposed to high concentrations of caustic solutions. Effects: corrosion may result in accelerated degradation and reduced mechanical properties. Number 4 is aluminum and aluminum alloys. Aluminum and aluminum alloys corrosion behavior: aluminum is generally resistant to corrosion, however, it can be susceptible to caustic corrosion, particularly in concentrated alkaline solutions that can attack the protective oxide layer. Aluminum and aluminum alloys problems: caustic environments can lead to pitting and localized attack. Number 5 is nickel alloys. Nickel alloys use in corrosive environments: nickel-based alloys, such as Inconel, Monel, are often used in caustic environments due to their corrosion resistance. Nickel alloys limitations: while more resistant than carbon steels and stainless steels, certain nickel alloys may still experience caustic corrosion under specific conditions, particularly at elevated temperatures. Number 6 is titanium. Titanium general resistance: titanium exhibits good resistance to a wide range of corrosive environments, including alkalinity. However, in some high-stress conditions or at elevated temperatures, caustic corrosion can occur. Titanium applications: while less common, caustic corrosion can affect titanium components in specialized applications. Number 7 is cast iron. Cast iron corrosion issues: cast iron can suffer from caustic corrosion, especially in its more porous forms. Extended exposure can lead to significant degradation. Cast iron wear and tear: the weakened structure may lead to cracking or failure over time. Understanding the susceptibility of these materials to caustic corrosion is crucial in industries such as chemical processing, pulp and paper manufacturing, and oil and gas. Selecting appropriate materials and employing effective protective measures can help mitigate the risks associated with caustic corrosion. Caustic corrosion critical factors based on API 571. Major contributing factors are the presence of caustic, NaOH or KOH. The following are sources of caustic. Number A. Caustic is sometimes added to process streams for neutralization or as a reactant. Number B. It is sometimes intentionally added to boiler feedwater at low concentrations or may enter inadvertently during regeneration of demineralizers. Number C. Alkaline salts may also enter process streams through leaks in condensers or process equipment. Number D. Some process units utilize caustic solutions for neutralizing, for removal of sulfur compounds, or for removal of chloride compounds. Number E. A concentrating mechanism must exist to build up the caustic strength. Number F. Caustic may become concentrated by departure from DNB, evaporation and deposition. The occurrence and severity of caustic corrosion damage are influenced by several critical factors. Understanding these factors is essential for predicting corrosion behavior, preventing material degradation, and ensuring the longevity and safety of equipment and structures exposed to caustic environments. Here are the caustic corrosion damage key critical factors. Number 1 is pH level. Alkaline concentration. Caustic corrosion is most pronounced in environments with high pH levels, especially above pH 12. Higher concentrations of hydroxide ions, OH, increase the corrosivity of the solution and contribute to accelerated metal degradation. Number 2 is temperature. Increased reaction rates. Elevated temperatures can accelerate the corrosion process by increasing the kinetic energy of chemical reactions. The rate of caustic corrosion typically increases with temperature, leading to faster degradation of materials. Number 3 is material properties. Material selection. Different materials have varying susceptibilities to caustic corrosion. For instance, carbon steel is more vulnerable than certain stainless steels or nickel-based alloys. The alloying elements and microstructure play vital roles in determining the corrosion resistance of a material. Number 4 is concentration of caustic solution. Higher concentration effects. The presence of concentrated caustic solutions can lead to more severe corrosion than diluted solutions. The concentration of hydroxide ions directly influences the corrosion rate and the severity of damage. Number 5 is stress and strain. Stress corrosion cracking. The presence of tensile stress in materials, whether from operational loads or environmental factors, can lead to localized phenomena like stress corrosion cracking, SCC, when combined with caustic environments. This can significantly undermine structural integrity. Number 6 is duration of exposure. Cumulative damage. Prolonged exposure to caustic environments increases the likelihood of corrosion damage. Over time, even materials with good initial resistance can suffer significant degradation. Number 7 is presence of oxygen. Aeration effects. The presence of oxygen can exacerbate the corrosive process by facilitating electrochemical reactions. Oxygen can promote the formation of rust in iron or enhance corrosion in various metals interacting with caustic solutions. Number 8 is electrolyte characteristics. Conductivity and composition. The conductivity of the caustic solution and the presence of impurities or other ions can influence the rate and nature of corrosion. For example, certain anions, like chlorides, can lead to synergistic effects, increasing corrosion rates. Number 9 is surface conditions. Surface finish and coatings. The condition of the material's surface, including roughness, presence of coatings, and any protective barriers, can significantly impact the rate of corrosion. Smooth surfaces may resist corrosion better, while rough or damaged surfaces can promote localized attacks. Number 10 is fluid dynamics. Flow conditions. The nature of fluid flow, laminar versus turbulent, and stagnation can influence corrosion rates. Turbulent flow typically increases mass transfer and can lead to higher localized corrosion rates, while stagnant areas may see more localized attack due to depletion of protective layers or accumulation of corrosive species. Number 11 is chemical additives. Inhibitors. The addition of corrosion inhibitors or other chemicals can modify the corrosive behavior of caustic solutions. Inhibitors can form protective films on the metal surface, reducing the impact of caustic corrosion. Understanding these factors allows engineers and maintenance personnel to implement effective strategies to mitigate caustic corrosion, enhancing the durability and reliability of materials and components in caustic environments. Caustic corrosion affected units or equipment based on API 571. Number A. Caustic corrosion is most often associated with boilers and steam generating equipment including heat exchangers. Number B. Similar concentrating effects of caustic may occur where caustic is added to crude unit charge. Number C. Accelerated localized corrosion can occur in preheat exchangers, furnace tubes and transfer lines, unless the caustic is effectively mixed in the oil stream. Number D. Units that use caustic for removing sulfur compounds from product streams, top of form. Caustic corrosion can impact a variety of units and equipment, particularly in industries that utilize alkaline substances. The specific types of equipment exposed to caustic environments often depend on the processes in which they are involved. Here are some common types of units and equipment that can be affected by caustic corrosion. Number 1 is pipelines and piping systems. Pipelines and piping systems description: transport liquids that may contain caustic solutions. Pipelines and piping systems risk: corrosion can lead to leaks, ruptures, and failures, potentially causing safety hazards and environmental damage. Number 2 is pressure vessels. Pressure vessels description: used to contain gases or liquids at high pressures, including caustic solutions. Pressure vessels risk: caustic corrosion can weaken the vessel walls, leading to catastrophic failures, especially if stress corrosion cracking occurs. Number 3 is storage tanks. Storage tanks description, designed to hold caustic chemicals or wastewater containing alkaline substances. Storage tanks risk, corrosion can lead to leaks or structural failures, resulting in environmental contamination. Number 4 is heat exchangers. Heat exchangers description, used to transfer heat between two or more fluids, often involving caustic solutions. Heat exchangers risk, corrosion can diminish their efficiency, lead to blockages, and result in failure due to thinning of tube walls. Number 5 is reactors. Reactors description, equipment designed for chemical reactions, sometimes involving caustic agents. Reactors risk, direct contact with caustic materials can lead to corrosion damage, impacting reaction efficiency and safety. Number 6 is boilers. Boilers description, used for generating steam or hot water, sometimes using caustic treatments in water systems. Boilers risk, corrosion can occur in the boiler tubes, leading to failures, leaks, or explosion risks. Number 7 is pump components. Pump components description, pumps that handle caustic fluids, including centrifugal and diaphragm pumps. Pump components risk, components like impellers and casings can corrode over time, leading to leaks and equipment failure. Number 8 is valves and fittings. Valves and fittings description, control the flow of caustic solutions in piping systems. Valves and fittings risk, corrosion can lead to valve failure, leaks, or faulty operation, impacting overall process safety. Number 9 is heat treating furnaces. Heat treating furnaces description, used in heat treatment processes, which may involve caustic cleaning solutions. Heat treating furnaces risk, corrosion of furnace components can affect the temperature uniformity and efficiency. Number 10 is distillation columns. Distillation columns description, used in separation processes that might involve caustic properties. Distillation columns risk, corrosion can affect the tray or packing materials, reducing separation efficiency and leading to structural issues. Number 11 is cooling towers. Cooling towers description, facilitate cooling of caustic solutions. Cooling towers risk, corrosion can affect parts such as fill media and water distribution systems, reducing cooling efficiency and longevity. Number 12 is scrubbers. Scrubbers description, used to remove pollutants from gases using alkaline scrubbing solutions. Scrubbers risk, corrosion of the scrubber's internal surfaces can lead to leaks and operational failure. Number 13 is centrifuges. Centrifuges description, employed in processes for separating materials with caustic interactions. Centrifuges risk, parts such as bowls and rotors may experience wear and tear from caustic exposure. Number 14 is measurement instruments. Measurement instruments description, sensors and gauges used for monitoring pH and other parameters in caustic environments. Measurement instruments risk, corrosion can lead to inaccurate readings or device failure, affecting process control. Proper design, material selection, and maintenance strategies are crucial to mitigating the risks associated with caustic corrosion in these types of equipment. This includes using appropriate coatings, corrosion inhibitors, and regular inspection and monitoring practices. Appearance or morphology of caustic corrosion damage based on API 571, Number A, typically characterized by localized metal loss which may appear as grooves in a boiler tube or locally thinned areas under insulating deposits, see Figure 499, ID deposits on CS boiler tube with damage due to caustic corrosion. See Figure 4100, cross-section of tube in Figure 499 showing localized attack due to caustic corrosion. Number B, deposits may fill corroded depressions and mask damage below. Probing suspect areas with a sharp instrument may be required. Number C, localized gouging may result along a waterline where corrosives concentrate. In vertical tubes, this may appear as a circumferential groove. Number D, in horizontal or sloped tubes, grooving may appear at the top of the tube or as longitudinal grooves on opposite sides of the tube. Number E, exposure to high solution strength caustic can result in general corrosion of carbon steel above 175 degrees Fahrenheit or 79 degrees Celsius, and very high corrosion rates above 200 degrees Fahrenheit or 93 degrees Celsius. Caustic corrosion can manifest in various forms, each exhibiting distinct morphological characteristics. Understanding the appearance of caustic corrosion damage is crucial for identifying issues early and implementing appropriate maintenance strategies. Here are the typical appearances and morphology associated with caustic corrosion. Number 1 is pitting corrosion. Pitting corrosion appearance: small, localized depressions or pits that penetrate the metal surface. The pits may vary in size and depth. Pitting corrosion cause occurs due to localized attacks, often exacerbated by the presence of contaminants and uneven flow conditions in a caustic environment. Number 2 is generalized corrosion. Generalized corrosion appearance: a uniform loss of material across a wide area, resulting in a dull or rough surface texture. The metal may appear to have a faded or oxidized appearance. Generalized corrosion caused by prolonged exposure to caustic solutions that uniformly attack the surface without localized effects. Number 3 is stress corrosion cracking, or SCC. Stress corrosion cracking appearance: visible cracks that can form on or near welds, joints, or areas of high stress. These cracks may appear as fine fissures or larger cracks, often following the grain structure of the metal. Stress corrosion cracking occurs due to the combined effects of tensile stress and a caustic environment, leading to crack propagation over time. Number 4 is intergranular corrosion. Intergranular corrosion appearance: darkened lines or zones along the grain boundaries, often leading to a network appearance. The surfaces may exhibit a granular or frosted look where the metal has been corroded. Intergranular corrosion results from the attack on the grain boundaries of certain alloys, particularly susceptible materials like stainless steel in caustic environments. Number 5 is uniform material loss. Uniform material loss appearance: smooth, well-defined edges around the corroded area. The metal surface may show a general reduction in thickness and a dull finish, without localized features. Uniform material loss often a result of consistent exposure to caustic solutions, affecting large areas of the surface evenly. Number 6 is erosion corrosion. Erosion corrosion appearance: a combination of pitting and grooves that appear on surfaces, often with a characteristic wash pattern indicating the action of fluid flow. Erosion corrosion this process occurs when mechanical wear from fluid movement enhances the effect of corrosive attack, frequently seen in areas of high turbulence. Number 7 is corrosion under insulation, or CUI. Corrosion under insulation appearance: discoloration, rust, or corrosion marks beneath insulation materials. This may not be visible until the insulation is removed. Corrosion under insulation moisture and caustic environments often become trapped underneath insulation, leading to localized corrosion. Number 8 is white rust formation. White rust formation appearance: a white, powdery deposit, often seen on galvanized steel. This deposit indicates corrosion, especially in caustic or humid environments. White rust formation formed by the reaction of zinc with caustic solutions, resulting in the corrosion of the zinc coating. Number 9 is surface roughness and discoloration. Surface roughness and discoloration appearance: increased surface roughness, with a mottled or uneven texture, often accompanied by discoloration, e.g., darkening, rusting. Surface roughness and discoloration non-homogeneous attack leading to localized loss of material and changes in the surface finish. In summary, the morphology of caustic corrosion damage can be characterized by various patterns, including pitting, generalized corrosion, and the presence of cracks or surface roughness. The key appearances associated with caustic corrosion include: pitting corrosion, localized pits on the metal surface. Generalized corrosion, uniform material loss and rough textures. Stress corrosion cracking, cracks that follow the grain structure. Intergranular corrosion, dark lines at grain boundaries. Erosion corrosion, grooves and wear patterns due to fluid flow. Corrosion under insulation, or CUI hidden corrosion beneath insulation. White rust formation, powdery white deposits on galvanized materials. Surface roughness and discoloration, dullness and uneven texture of the metal. Recognizing these morphological features is essential for assessing the extent of corrosion damage, planning maintenance, and selecting appropriate materials for caustic environments. Caustic corrosion damage prevention and mitigation based on API 571, Number A, in steam generating equipment, caustic corrosion is best prevented through proper design. Damage can be minimized by reducing the amount of free caustic, by ensuring adequate water flooding and water flow, by ensuring proper burner management to minimize hot spots on heater tubes, and by minimizing the ingress of alkaline-producing salts into condensers. Number B, in process equipment, caustic injection facilities should be designed to allow proper mixing and dilution of caustic in order to avoid the concentration of caustic on hot metal surfaces. Number C, carbon steel and 300 series SS have serious corrosion problems in high-strength caustic solutions above about 150 degrees Fahrenheit 66 degrees Celsius. Alloy 400 and some other nickel-base alloys exhibit much lower corrosion rates. Preventing caustic corrosion damage involves a combination of material selection, design considerations, operational practices, and maintenance strategies. Here are some effective prevention and mitigation techniques for caustic corrosion. Corrosion-resistant alloys, use materials that are inherently resistant to caustic corrosion, such as 304 or 316 stainless steel, those subject to limitations, especially at high temperatures or concentrations. Nickel alloys, such as Hastelloy, Monel, that have excellent corrosion resistance in caustic environments. Titanium and certain plastics, like PVC, HDPE, for specific applications. Surface coatings, apply protective coatings, such as epoxy, polyurethane, to create a barrier between the metal and the caustic environment. Number 2 is proper design. Avoiding traps, design piping and equipment layouts to minimize dead legs, stagnation points, and low-flow areas where caustic can pool and cause localized corrosion. Proper drainage, ensure that layout allows for proper drainage to avoid the accumulation of liquids that can cause corrosion. Weldments and joints, use high-quality welding techniques and keep joints and welds smooth and free of defects that can harbor corrosion. Number 3 is control of operational conditions. Temperature control, maintain lower operating temperatures where possible since higher temperatures can exacerbate caustic corrosion. Concentration management, dilute caustic concentrations when feasible to reduce corrosive effects on materials. Flow rate control, ensure adequate flow rates to prevent stagnant areas, but avoid excess turbulence that could lead to erosion corrosion. Number 4 is cathodic protection. Impressed current or sacrificial anodes, use cathodic protection systems to protect metal surfaces from corrosion, especially in buried or submerged applications. Number 5 is regular maintenance and monitoring. Inspection programs, implement regular visual and non-destructive testing, or NDT, inspection programs to detect early signs of corrosion. Thickness monitoring, use thickness gauges to monitor the integrity of critical components over time. Repair protocols, establish protocols for fast and effective repair of corroded areas to prevent failure. Number 6 is chemical additives and inhibitors. Corrosion inhibitors, add chemicals to the caustic solution that form protective films on metal surfaces, thereby reducing corrosion rates. pH control, maintain optimal pH levels to minimize corrosive environments, although care must be taken to avoid excessive alkalinity. Number 7 is insulation and environmental control. Proper insulation, utilize insulation materials that do not retain moisture and are resistant to chemical attacks. Ensure that they are applied correctly to prevent moisture accumulation. Humidity control, maintain low humidity levels in areas surrounding equipment to minimize the risk of corrosion. Number 8 is education and training. Employee training. Train staff on the hazardous effects of caustic environments and the importance of maintenance and inspection procedures. Number 9 is design for maintenance. Accessibility. Design systems to allow easy access for inspection and maintenance, enabling quick response to any signs of corrosion. In summary, effectively preventing caustic corrosion damage involves a multifaceted approach, including material selection. Use resistant alloys and coatings. Design considerations. Optimize layouts to avoid traps and stagnation. Operational controls. Manage temperature, concentration, and flow rate. Cathodic protection. Implement systems to reduce corrosion potential. Regular maintenance. Conduct inspections and monitor equipment. Chemical additives. Utilize corrosion inhibitors and monitor pH levels. Insulation. Ensure appropriate and moisture-resistant insulation. Education. Provide training for personnel on corrosion risks. By implementing these strategies, organizations can significantly reduce the incidence of caustic corrosion, prolonging the life of their equipment and ensuring operational safety. Caustic corrosion inspection and monitoring based on API 571, Number A. For process equipment, UT thickness gauging is useful to detect and monitor general corrosion due to caustic. However, localized losses due to caustic corrosion may be difficult to locate. Number B. Injection points should be inspected in accordance with API 570. Number C. UT scans and radiography can be used. Number D. Steam generation equipment may require visual inspection with the use of borescope. Detecting caustic corrosion damage requires a combination of visual inspection, non-destructive testing, NDT, methods, and monitoring techniques. Here are several effective inspection and monitoring methods commonly used. Number 1 is visual inspection. Visual inspection description. Regular visual inspections are often the first line of defense in identifying signs of caustic corrosion. Visual inspection. What to look for. Observers should look for pitting, discoloration, surface roughness, undercutting, and signs of stress corrosion cracking, especially around welds and joints. Visual inspection documentation. Taking photographs and maintaining inspection records helps in tracking changes over time. Number 2 is ultrasonic testing, or UT. Ultrasonic testing description. Ultrasonic testing uses high-frequency sound waves to measure the thickness of materials and detect flaws. Ultrasonic testing application. It is particularly effective for identifying pitting and general corrosion, as well as monitoring the thickness of critical components over time. Ultrasonic testing advantages. This method is non-invasive and provides precise measurements of wall thickness. Number 3 is radiographic testing, or RT. Radiographic testing description. This method involves the use of X-rays or gamma rays to produce images of the internal structure of components. Radiographic testing application. It is useful for detecting internal defects, such as cracks or voids, which may not be visible via external inspection. Radiographic testing limitations. It may not be as effective for detecting low-density areas created by corrosion. Number 4 is magnetic particle testing, or MT. Magnetic particle testing description. This method detects surface and near-surface discontinuities through the use of magnetic particles. Magnetic particle testing application. It is valuable for identifying cracks or flaws on ferromagnetic materials. Magnetic particle testing advantages. Quick and effective for detecting surface cracks. Number 5 is dye penetrant testing, or PT. Dye penetrant testing description. A liquid dye is applied to the surface, and after a dwell time, it is drawn out of imperfections by a developer. Dye penetrant testing application. Effective for detecting surface breaking defects like cracks and pits. Dye penetrant testing limitations. It is not suitable for use on porous materials or where heat treatment has been applied. Number 6 is eddy current testing, or ECT. Eddy current testing description. Eddy currents are induced in conductive materials, and the response is measured to detect corrosion in cracks. Eddy current testing application, useful for nonferromagnetic materials and for measuring wall thickness without contacting the surface. Eddy current testing limitations, sensitivity can be affected by surface conditions and cleanliness. Number 7 is electrochemical methods. Electrochemical methods description, in situ techniques, such as linear polarization resistance, LPR, and electrochemical impedance spectroscopy, EIS, can be used to assess corrosion rates. Electrochemical methods application, these methods provide real-time monitoring of corrosion rates in caustic environments. Electrochemical methods advantages, they allow for early detection of corrosion processes and can help in assessing the effectiveness of corrosion inhibitors. Number 8 is corrosion monitoring probes. Corrosion monitoring probes description, installed probes measure electrical resistance or other parameters to provide continuous monitoring of corrosion. Corrosion monitoring probes application, can be placed in representative locations within the system to give real-time data on corrosion rates. Corrosion monitoring probes advantages, useful for ongoing monitoring to detect corrosion trends over time. Number 9 is thickness gauges and monitoring systems. Thickness gauges and monitoring systems description, digital thickness gauges can be used to periodically measure wall thickness at critical points. Thickness gauges and monitoring systems application, automated monitoring systems can continuously measure the thickness of materials to identify trends indicating corrosion progression. Thickness gauges and monitoring systems advantages, provides continuous data to anticipate maintenance needs. Number 10 is infrared thermography. Infrared thermography description, this non-contact inspection method uses infrared cameras to detect temperature differences caused by corrosion or insulation failures. Infrared thermography application, useful for identifying areas of heat loss or abnormal thermal patterns that may indicate underlying corrosion or moisture intrusion. Infrared thermography advantages, quick and effective for assessing large areas. In summary, combining these inspection and monitoring methods allows for a comprehensive approach to detecting caustic corrosion damage. Visual inspection, regular checks for surface signs. Ultrasonic testing, non-invasive thickness measurement and flaw detection. Radiographic testing, X-ray imaging of internal structures. Magnetic and dye penetrant testing, detecting surface and near-surface defects. Eddy current testing, non-invasive detection in conductive materials. Electrochemical methods, real-time corrosion monitoring. Corrosion monitoring probes, continuous assessment. Thickness gauges, regular measurement of wall thickness. Infrared thermography, identifying thermal anomalies linked to corrosion. Using a combination of these methods can provide reliable data for assessing the condition of materials exposed to caustic environments, ensuring timely maintenance and safety in operations. Thank you.